Hi everyone! Today we're going to talk about how to solve a three-dimensional Lagrange multiplier problem with two constraints. To complete this problem, we'll take partial derivatives of our original function as well as each of our constraint equations, solve for two multipliers and three variables, and then evaluate the original function at the point that we found. Let's take a look. In this particular problem, we've been asked to use Lagrange multipliers to find any extrema of the function f of x, y, z if it's equal to x squared plus y squared plus z squared. Also, subject to two constraint equations, the first of which is x plus y plus z is equal to 1, and the second of which is x plus 2y plus 3z is equal to 6. So the first thing we always want to do with any Lagrange multiplier problem is make sure that our constraint functions are in terms of, in this case, g of xyz and h of xyz. So our original function is f, so we'll make our two constraint functions g and h. The way that we're going to do that is by subtracting the constants on the right-hand side over here from both sides to move everything to the left-hand side. So what we'll get is g of xyz, this first constraint equation here becomes g of xyz is equal to x plus y plus z minus 1. So we just subtracted 1 from both sides to move everything to the left. Same thing here, h of xyz will be equal to x plus 2y plus 3z minus 6. So 3z minus 6, we just subtracted 6 to move it to the left-hand side. So those are our two constraint equations. Now our second step is going to be to take partial derivatives with respect to all three variables of all of our functions. So our original function f of xyz and our two constraint equations. So what we'll do is we'll get ourselves a little kind of table here going. We'll say the partial derivative of f with respect to x, the partial derivative of f with respect to y, and the partial derivative of f with respect to z. Then we'll go over here and say the partial derivative of g with respect to x, partial derivative of g with respect to y, and the partial derivative of g with respect to z. And we'll need the same thing over here for h. So now we need to take the partial derivatives that we've written down here. So the partial derivative of f with respect to x, remember that when we're taking the partial derivative with respect to x, we're treating y and z, the other variables, as constants. So the partial derivative here of x squared is 2x. If y and z are constants, then the partial derivatives of y squared and z squared, when we're taking the derivative with respect to x, will be 0. So same thing here when we take the partial derivative with respect to y, x and z are constants, so they become 0. We're just left here with 2y, and of course here 2z when we treat x and y as constants. Now we're looking for the partial derivatives of x, y, and z, or of g with respect to x, y, and z. So again, treating y and z as constants, the derivative of x is just 1. The derivative of y will be 0, z will be 0, and of course the constant -1 will be 0. And when we apply that to the partial derivative of g with respect to y, we again get 1 because x will be 0, y will be 1, z is 0, and again the constant is 1. And of course we get the same thing for z. Our partial derivatives of h with respect to x, y, and z, you can see here, y, z, and the -6 will all become 0 when we take our derivative. The x will be 1. When x and z are treated as constants and we take the partial derivative with respect to y, we'll get 2 because that's the coefficient on our y term here. And then z will be 3, the coefficient on the term here that includes z. Once we have all of our partial derivatives calculated, we're going to go ahead and set up our Lagrange multiplier equations. So the way that we'll do that is we'll take the partial derivative of our original function here, f, so we'll take 2x, and we'll set that equal to whatever we got for the partial derivative of g times lambda. So in this case, 1 times lambda is just lambda, plus whatever we got for our partial derivative with respect, our partial derivative of h times mu. So 1 times mu is just going to give us mu here. We'll set up the other two equations, and you're always going to set partial derivatives of each function with respect to x equal to one another, and then take all of the partial derivatives with respect to y and set them up in your Lagrange multiplier equation, and then the z's together. So again, here for the y's, we'll get 2y is equal to 1 times lambda is just lambda, plus 2 times mu, so 2 times mu. Then you'll put all the z's into a equation, and you'll get 2z, the partial derivative of f with respect to z, is equal to, again, 1 times lambda plus 3 times mu, so 3 times mu, like this. And those are the 3 Lagrange multiplier equations that we'll be working with going forward. After you get these equations set up, your next goal is going to be to solve each one for x, y, and z are 3 variables. So as you can see, the first equation here, we'll just divide both sides by 2, and we'll see that x is equal to lambda plus mu, all divided by 2. We'll do the same thing for y and z here. We'll divide both sides by 2 because we're trying to solve for the variable, and we'll get y equals lambda plus 2 mu over 2, and then z, we'll get z equals lambda plus 3 mu over 2. So now that we have values for x, y, and z, we want to go ahead and plug them into our constraint equations here. So x plus y plus z equals 1. We'll plug in the values of x, y, and z here for x, y, and z and set that equal to 1. We'll do the same thing here with our second constraint equation. But let's go ahead and plug it into the first constraint equation. So we'll get lambda plus mu over 2 for x plus lambda plus 2 mu over 2 for y plus lambda plus 3 mu over 2 for z is equal to 1. Again, we just plugged in x, y, and z into our first constraint equation here. What we want to go ahead and do with this is simplify it so that we have an equation in terms of lambda and mu. So we'll go ahead and multiply both sides by 2 to get rid of the fractions, and we'll be left with lambda plus mu plus lambda plus 2 mu plus lambda plus 3 mu is equal to 2. And now when we add these together, we'll get 3 lambda plus 6 mu is equal to 2. Now we'll go ahead and do the same thing with our second constraint equation, plugging in x, y, and z, and then simplify it to get an equation in terms of lambda and mu. Now we'll go ahead and distribute the 2 across this fraction here and the 3 across this fraction. And now we'll multiply both sides by 2 to cancel the fractions. And now we'll just combine like terms to simplify. We'll go ahead and divide through this equation by 2 to simplify. So we'll get 3 lambda plus 7 mu is equal to 6. And now what we want to do is use the equation here and here to solve for lambda and mu. So what we'll do is we'll bring this out over here, plus 6u equals 2, and then we have 3 lambda plus 7 mu equals 6. We'll go ahead and subtract the second equation from the first one. When we do that, we'll get 3 lambda minus 3 lambda, which is just 0. 6 mu minus 7 mu is a negative mu, and 2 minus 6 gives us a negative 4, which means that we're going to get mu equal to positive 4. If we plug that back into our first equation here, we'll get 3 lambda plus 6 times 4 for mu is equal to 2. 3 lambda plus 24 equals 2. 3 lambda is equal to negative 22, which means that lambda is equal to negative 22 thirds. And now that we have values for mu and lambda, we want to go ahead and plug those into the right-hand sides of our equations for x, y, and z in order to solve for the values of x, y, and z. To go ahead and make this easier, let's go ahead and say that this 4 here, if we multiply by 3 over 3, which is essentially multiplying by 1, we'll get 12 over 3. Having a common denominator with our value for lambda will make it easier for us to solve for x, y, and z. So we'll get that x is equal to lambda, so negative 22 thirds, plus mu, plus 12 thirds, all over 2. When we simplify this, negative 22 plus 12 will give us a negative 10 thirds divided by 2. That's the same thing as negative 10 thirds times 1/2, which will give us negative 10 over 6, which is negative 5 thirds. So we get that x is equal to negative 5 thirds. When we plug these in for y, we'll get y equals, again for lambda, negative 22 thirds plus 2 times mu. So 2 times 12 over 3 is going to be 24 over 3, all divided by 2. And what we'll get here is a positive 2 thirds divided by 2, which is the same thing as 2 thirds times 1/2. And we get a value of 1/3, so we can see that y is equal to positive 1/3. And for z here, again, we'll get lambda of negative 22 thirds plus 3 times mu, which will be 36 over 3, all divided by 2. That, of course, gives us a positive 14 thirds over 2, which is the same as 14 thirds times 1/2, which will give us 14 over 6, which is, of course, the same as 7 over 3. So we see that z is equal to positive 7 thirds. Okay, so our last step, now that we've solved for x, y, and z, is going to be to plug those values back into our original function, f of x, y, z. So this set of points here, or this set of values, constitutes the coordinate point negative 5 thirds, 1/3, 7/3. So essentially we're plugging in that point, we're evaluating the function at that point to see what the value is. So we'll say f of negative 5 thirds, 1/3, 7/3 is equal to, of course here we'll square negative 5 thirds, so 5 thirds squared plus 1/3 squared plus 7 thirds squared. When we simplify here, we'll get 25 ninths plus 1/9 plus 49 ninths. And when we add these together, we'll get 75 over 9, which when we divide both numerator and denominator by 3, we'll get 25 thirds. At this point, we know that 25 thirds is the value of the function at its extrema. All we need to do now is figure out whether or not 25 thirds is a maximum or a minimum value. And luckily, it's relatively easy for us to do that in this case because we know that f of x, y, z, this function here, x squared plus y squared plus z squared, is the standard equation of a paraboloid that opens up, right? So it's roughly, a parabola, you can kind of think of it as a 3D parabola like this in an XYZ three-dimensional coordinate system like this, right? The paraboloid that opens up. So 25 thirds, we know, must be a minimum of the function. There is no maximum of the function because this paraboloid increases forever upwards without bound. So we know that 25 thirds is a minimum and that there is no maximum of the function. So that's it. That's how you use Lagrange multipliers to find extrema of the function and determine whether or not those values are minimum values or maximum values. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.